I'm Holly, and I will be talking about sublethal doses of insecticide reduce critical thermal maxima of a stingless bee. So, before I begin, I would just like to acknowledge the Yurunganji people, traditional custodians of the land on which I stand today and also conducted my research on. And I pay my respects to the elders, past and present, and extend that respect to Aboriginal and Torres Strait Islander peoples here today. So, let's get into it. Insects are threatened by a range of stresses, including insecticide exposure and climate change. And climate change has the potential to cause events such as heat waves that may cause heat stress in insects. And while both insecticide exposure and heat stress have been studied in insects, um, very little studies have investigated the interaction between the two. So some studies have found that temperature increases insecticide toxicity. For example, exposing the silverleaf whitefly, Bemsia tabaci biotype Q, to temperatures of 35 degrees and above resulted in decreased tolerance to the insecticide thiamethoxam in comparison to exposure to 31 degrees. Another study found that the mosquito, Aedes aegypti, and the aquatic crustacean, Daphnia magna, were less tolerant to the insecticide terbufenicide at 27 degrees compared to 20 degrees. However, to the best of our knowledge, only one study has quantified this relationship between insecticide exposure and heat stress over a dynamic range of temperatures. So this was the preprint study over here by Gonzalez, and they tested on Apis mellifera and actually found that acute exposure to the neonicotinoid insecticides imidacloprid and acentemiprid increased the critical thermal maxima of the bee. And critical thermal maxima is a measure of the highest temperature at which an organism can maintain neuromuscular function. So given the conflicting trends of the interactions between insecticide and heat stress on insects in the literature, as well as the lack of information specific to bees, especially stingless bees, we asked the question, do sublethal doses of insecticide influence the critical thermal maxima of a stingless bee? So we chose the Australian stingless bee species Tetragonial hockingsi as they are locally widespread. This is a diagram, just a rough diagram of their distribution. And they're locally widespread in the wet tropics, which is where I'm located up here. They also possess common stingless bee traits, such as being active year-round and nesting in cavities. And they may also provide potentially important pollination to local crops, such as mangoes, avocados, strawberry, and coffee. So let's get into the methods. This was the sample size that we used. And we collected bees from the Cairns Botanic Gardens indicated on this map. And we collected 30 bees per experiment by placing a container to the entrance of the hive and collecting the exiting forages. We then transferred them to a temperature control cabinet for a 24-hour acclimatization period. And after this period, we transferred the bees to individual vials where we fed them treatment doses within sucrose using a micropipette. And the doses, the treatments that we used included a sucrose control and then sucrose laced with different concentrations of insecticide. So the insecticides that we used were imidacloprid and fipronil, and we chose them because they're commonly used. They have been implicated in mass mortalities. They can be systemic, and it's easy for bees to be exposed to them in the nectar and pollen of treated crops. So this table shows the doses that were used for both insecticides, and the doses were based on what had previously been used in the literature on different bee species, and then scaled down to the body mass of Tetragonial hockingsi. We also piloted each dose to ensure that they were truly sublethal, and doses were also relevant to field residue data available. So after receiving the treatments, bees were held at a constant temperature of 27 degrees for 6 hours. After that, they were transferred into a water bath in their individual vials, which we made over here by attaching a temperature controlled immersion heater to a bucket filled with water with a vial rack inside. And to determine the critical thermal maxima of tetragonial Hawkingsi, we use the widely used method of ramping a temperature increase from an ambient temperature at a set rate. So we ramp from 27 degrees at intervals of half a degree every 2 minutes until the critical thermal maxima of each individual was reached. And we determine the critical thermal maxima as the point at which an individual became unresponsive to stimulus. And we also kept 14 bees that had received the same insecticide treatments at a constant temperature of 27 degrees, just to assess whether mortality would occur due to insecticide treatment alone and not to do with the temperature. And over all of our experiments, we had a 100% survival rate. All right, so onto some results of our imidacloprid experiments. So on our x-axis, we have our treatments, we have our doses in nanograms per bee of imidacloprid, and then our control. And on our y-axis, we have our critical thermal maxima in degrees Celsius, and then we also have some confidence intervals on here as well. So in comparison to the sucrose control, we found a significant reduction in critical thermal maxima for bees that received the medium dose and also the high dose of imidacloprid. And to put that into perspective and show you how big that reduction was, if we look at the control compared to the high dose, there was about a 1.5 degree reduction in critical thermal maxima. So then if we then jump back to the study that I showed you at the start, that looked at critical thermal maxima in Apis mellifera when they'd received imidacloprid, we can see that our results actually contrast that. And this could be due to many different factors, possibly physiology, metabolism, or body size between the two species. And this difference just highlights the importance for studying this interaction across different species. If we then take a look at our fipronil experiments, again, on our x-axis, we have our treatments and our y-axis, our critical thermal maxima. When comparing between the control and the low, medium, and high, we can see that the low, medium, and high had a significantly reduced critical thermal maxima. And again, to put that into context, between the control and the high, there was around a 1.3 degree reduction in critical thermal maxima. So let's have a look at a potential mechanism. The effect of insecticide exposure on thermal tolerance could potentially be driven by physiology or metabolism processes in bees. For example, heat stress can affect metabolism by disrupting the balance of detoxification enzyme systems that work to help resist damage caused by metabolic poisons and harmful substances such as insecticides. And while this is just one potential mechanism, further research into mechanisms is warranted. So before I dive deeper into the implications of this study, I want to quickly address the caveats to directly applying these critical thermal maxima values to bees in the field. So firstly, bees in the study couldn't move. They were held in vials. They weren't in their natural conditions. And the experiment also facilitated a more rapid increase of temperature than natural conditions would in most cases. And bees were taken out of their social setting where they'd usually employ thermoregulation strategies, such as fanning of wings, or be inside their insulated hives. But we can conclude some things. These temperatures are still very relevant to what would be experienced in the field. And we can take them as a proxy. And also bees that would be foraging outside of the nest could be likely to experience these effects if they're not in their hive. So what do our results mean in a field context? Well, it's possible that bees will be exposed to temperatures that may exceed their critical thermal maxima in the field. And if they've previously been exposed to insecticide, this effect may be more pronounced. For example, in 2018, the city of Cairns, shown on this map, experienced an extreme heat event where a daily temperature of 42.6 degrees was recorded. So, if we then have a look back at our findings, we can see that our critical thermal maxima of control bees was above this daily temperature. So, perhaps those bees wouldn't be so affected. Um, However, when looking at the high doses of insecticide, we can see that exposure to insecticide caused a reduction in critical thermal max in the range of this heat wave. So it's possible that um, bees that have been exposed to similar doses of insecticide before this event may have been at a high risk. And while this is just a hypothetical situation, and this wouldn't necessarily be the case for all Tetragonella hawkingsi in the field, and maybe we can't put an exact figure on this relationship, we can predict that exposure to insecticide may lower critical thermal maxima. And this interaction is particularly worrying given that the frequency and severity of extreme heat waves is predicted to increase in the coming years with climate change, whilst insecticide use is also predicted and is also increasing with agricultural intensification. So, going into the future, to help predict how stingless bees and other bees will respond to stresses, it will be important to conduct studies to answer some of these questions. The first one is, which bee traits and elements of physiology are good predictors of responses to combined stress of insecticide exposure and heat stress? Do other insecticides and other concentrations result in the same responses or different responses? And do other bee species have the same responses? And just to finish up, I would like to thank everyone who's made this study possible, particularly my supervisors, Dr. Laurie Locke and Dr. Peter Yales, and my lab group, everyone at JCU, and Skyrao Rainforest Foundation for the funding, Ros Glowag for the bee identification, and Steve Williams for providing his precious bees to me. Thank you.
Thanks a lot, Holly. Very, very nice, and some really significant results there, it looks like. Well done. Have we got a
Thank you.
question for Holly? Got a couple of minutes, I think. You can just unmute if you like or write it in the chat. I'll give you 10 seconds. All right, here we go. Can you see that one, Holly? I assume as well that this
Oh,
might
yeah.
be. Oh, yeah. Oh, not really a question. That's okay. I wanted to ask Holly. Those bee people, the people who did the study on honeybees, they found the reverse, that increased insecticides helped their thermal tolerance. Did I see that correctly?
Yeah, that's
How
correct.
did they explain that? That sounds very odd, but how did
Yeah,
they?
so they actually set out, like they hypothesized that insecticide exposure would lower the critical thermal maxima, but they found the opposite. And they attributed it to like some kind of heat shock reaction. Um, but again, that is a preprint study from 2020. So whether or not it's going to be published or is repeatable or anything is another question. But yeah,
Okay.
there isn't any other studies like it.
Yeah. Oh, it's a really nice piece of work. Thank you. So, might move on, and thanks for getting us back on time, Holly. Ooh, okay, let's take this one. Quick one from Laura Fagan. What would you recommend the APVMA do knowing what you know now? Given that, yeah, you can read it there.
Yeah. Well, I think it would definitely need to be tested on perhaps a different scale, a bigger scale with more species. But I certainly found a significant effect. So it is worrying that bees can be exposed to these compounds out in nature and then be exposed to heat. Um, and I definitely hope that the APVMA does make some changes in the way that pesticides are regulated, but I don't have any specific recommendations.
Yeah, I think
Definitely, yeah, we need more work. hopefully this adds to the body of work.
Yes, they need to hear about your work, I think. So thanks very much, Holly. We better move on now.